Okay, in this video, we're going to learn about the elemental families. So, what we've learned about the trends, and we've learned about the properties of these elements. So, let's think about how this results in the different elements that we see across the periodic table. We're going to learn about the various groups, or we don't want to call them groups because there's group one, group two, so we don't want to get confused. So, we call them families. Here's the alkaline metal family, the alkaline metal family, transition metals, noble gases, metalloids, halogens, etc. So let's start as quickly as we can. Properties of metals. Metals are to the left of the periodic table. They're good conductors of heat and electricity. They're shiny, they're ductile, they're malleable, and they um, they generally react with water. First, maybe as corrosion, but if it's very reactive, it might even burn. Right. So, why do metals have these properties? Well, if you think about electronegativity, a very low electronegativity, as you move less left across the periodic table, this low electronegativity means that electrons can bounce very free. They're not very attached to those atoms. Remembering low electronegativity means that doesn't attract electrons very easily. So those electrons can move very freely from atom to atom to atom. And that creates a sea of electrons, a sea that just kind of floats from atom to atom to atom. And that results in a good conductor of electricity and heat. Those electrons can move very freely from one side of the atom of the metal to the other side because they're flowing very easily. They're shiny because photons coming in, light coming in, is going to bounce off electrons on the surface of the metal rather than having to go deep into the substance of the metal, like or substance of the material, like it would with an element that was holding onto its electrons very tightly. They're ductile and malleable. They can be bent and stretched into wires and pounded and whatever else. And that's because there's no fixed bonding structure. This sea of electrons is almost like a gloopy glue holding the elements together. It doesn't matter whether the nucleuses are in a straight line. Doesn't matter if they're all over the place. This gloopy kind of sea of electrons is going to hold them all together. And they're very reactive with metals, with water, just because of their nature. Alkali metals, you can see them here. Alkali metals have a single electron. They're out of my shell. Because remember, group 1 has 1 electron, group 2 has 2 electrons in the outer shell, group 13 has 3 electrons in the outer shell, group 4, 5, 6, 7, 8. They're shiny, they have the consistency of clay. You can kind of squash them and easily cut with a knife. The alkali metals are easily the most reactive metals. You throw them into water, have a bit of fun, and watch them explode. Okay. Alkaline earth metals, on the other hand, are generally never found uncombined in nature. Well, that means that they're always, when we see them in nature, they're always in some kind of ionic form. So they have 2 valence electrons, magnesium, calcium, etc. But again, relatively soft. You think about calcium, you think about magnesium, they're a relatively soft metal. Transition metals in the middle are mostly going to be ignored because they're too complicated. We don't like to talk about the electron structure of transition metals. We don't like to talk about the properties of transition metals because it's awfully complicated, and we're going to learn more about that in Year 11 Chem. But just know that most of the metals you're familiar with are in here: copper, tin, zinc, iron. So these tends to be the stronger, harder kind of metals that we are familiar with. Good conductors of heat and electricity, and yeah. So the compounds of transition metals are also often the brightly coloured ones, used to colour paints and things like that as well. I'm going to ignore that one. Okay, properties of metalloids. Metalloids are those elements between the metals and the non-metals. And I want you to think, if you think about that, what that's really saying is it's kind of on that barrier between where the electronegativity wants to attract to a certain strength, but not so strongly the metal would sorry, not so strong as a non-metal would, and not so weakly as a metal would. So it's got some properties, but not all the properties. They can be shiny or dull. They can conduct heat and electricity, but better than non-metals, but not as well as metals. They're ductile and malleable. So you think about silicon, think about carbon, think about things like that. Relatively, carbon's like brittle. Um, but it conducts electricity, right? In some forms, right? Your graphite pencil can conduct electricity, but a diamond, which is also carbon, can't. So they're a bit kind of in the middle. Non-metals, they don't conduct electricity or heat because they're holding onto those electrons. There's no sea of electrons anymore. They're all holding onto them in distinct bonds. They're not ductile, not malleable. They tend to be brittle. You break them. Think about glass or think about rocks. You break them. Um, in fact, many of them are gases. But I don't want you to feel like, every now and then I hear this misconception that says that non-metals are gases and metals are solids. It's nothing to do with that. Certainly have solid non-metals. After all, there's a picture of sulfur, very obviously a solid. Halogens in this 17th group, 7-valence electrons, the most active non-metals because they're going to attract the electrons very readily. And in fact, what you find is when combined with hydrogen, they make the best acids: hydrogen fluoride, hydrogen chloride, hydrochloric acid, right? Hydrogen bromide. These are very strong acids. Halogen groups need only one electron to fill their own mass group, so we're talking about that octet rule. They react with alkali metals to form salts. Noble gases we talked about, colorless gases, unreactive. They already have the full outer shell, so they don't need to react. Readily combine with other elements to form compounds. So they don't readily combine because they're completely inert. So we're talking about helium, argon, neon, krypton, xenon, radon. They're very small amounts on Earth's atmosphere. And finally, if we're talking about the lanthanides and actinides, very rare, often called transuranium because they're synthetic. Most of them, the universe simply, if you know anything about space, the universe simply isn't old enough to have created elements of this size. If you think about hydrogen burning in the sun and then blowing up and then spreading hydrogen and helium and working right up to carbon, then those things come together in the in the surface, in the center of another sun, which would burn iron as an iron core, as a larger sun, and then that would explode to create even larger elements. The Earth simply isn't old enough to have created this suns exploding and re-coming together to form more elements such that you're going to get these lanthanides and actinides. But we have managed to create them in the laboratory for minuscule periods of time, and they have various variety of properties. That's it. Answer the question below, and I'll see you in class.